mentioned, my name is Robin, and I'll talk about our work on unconventional field-like spin-orbit torques in chromium-platinum-3. So to start off, I'll just very briefly review spin-orbit torques in general. So if you have a spin source, which is typically a heavy metal like platinum or tungsten, and you send a charge current through that spin source, you generate a spin current in the z direction, with the charge current is in the x direction due to the spin Hall effect. And the spin polarization of the spin current is in the y direction. And the direction of the spin current is restricted, the spin polarization is restricted to be in this way by the symmetry of the spin source layer. So if you now put a ferromagnetic layer on top of the spin source, you can get an anti-damping torque on the magnetization of the ferromagnetic layer, which is sufficient for field-free deterministic switching of in-plane magnetization only in the y direction. So you can field-free deterministically switch from negative y to positive y, or vice versa, but you can't do any deterministic switching in the z or x direction with this kind of spin polarization. So people have been investigating if we can get unconventional spin polarizations in different directions to create torques that are efficient for switching in the other two directions. And one way that this has been looked at is through ferromagnetic ordering. So ferromagnets give rise to spin polarization that is along the magnetization direction, and thereby you can reorient the spin polarization by reorienting the magnetization direction. So this has been shown here, where on the left they just have tantalum, cobalt iron boron, which is just spin source and ferromagnet like before, and they compare this to a ferromagnetic trilayer with titanium in the middle, and they see differences in the spin polarization and the resulting spin torques. And there are from some other papers where similar effects have been seen. So the material that we're interested in is chromium-platinum-3 for several reasons. So the first one is that magnetic ordering may give rise to unconventional torques, just like in the ferromagnetic case. And I should mention that chromium-platinum-3 is a topological semi-metal. So it's, yeah. And the second reason is that there's a large spin-orbit coupling due to the platinum in the chromium-platinum-3. Thirdly, it can be made magnetic or non-magnetic. So as I said, it's ferromagnetic in the magnetic phase, and then there's a different phase where it's non-magnetic. So we can directly compare the role of magnetism in the torque generation. And fourth, it has a very large anomalous Hall effect due to its topological band structure. And then finally, it has high coercive field, so the magnetization can be set with a large magnetic field and then not changed during the measurement. So we can take a look at the spin torques generated with different coercive field saturations. So to generate or to grow this material, we used co-sputtering from chromium and platinum targets onto 220 oriented MgO substrate at 500 degrees Celsius to achieve 110 oriented chromium-platinum-3. And this gives us the chemically disordered chromium-platinum-3, where the chromium and platinum atoms are randomly distributed on the FCC crystal structure. And in this case, it's paramagnetic. And then when we add a 40-minute in situ post-annealing step at 850 degrees Celsius, we get chemically ordered samples, where in this case, the chromium atoms always occupy the corners of the cubic cell, and the platinum atoms always occupy the face-centered sides. And in the chemically ordered phase, the chromium-platinum-3 is ferromagnetic. But note that the crystal structure is still the same between chemically disordered and ordered. They're still both FCC crystals. Only the chemical ordering and the magnetism is different. So to characterize the films, we used X-ray diffraction, and for the disordered chromium-platinum-3, we see only the 220 peak, and there's no 110 peak. But for the ordered chromium-platinum-3, we also have this ordered, this 110 peak, which is only allowed for an ordered crystal, and not for a disordered one. Then we did in-plane X-ray diffraction measurements to confirm that the films are epitaxial, and we see the twofold symmetry of the chromium-platinum-3 and the well-aligned peaks with the substrate. So that confirms that we have epitaxial films. And finally, we looked at the magnetization. So we did magnetometry measurements, and we see that we have the magnetic easy axis along the 1 bar 1 0 direction, which is in plane for our 110 oriented chromium-platinum-3. And we see a relatively large coercive field on the order of 0.3 Tesla. So then we moved on to spin torque measurements, and we used spin torque ferromagnetic resonance for this. So we patterned chromium platinum 3, copper, and permalloy, where the permalloy acts as the ferromagnetic layer. The copper is a spacer to magnetically decouple the chromium platinum 3 from the ferromagnet, and then the chromium platinum 3 is the spin source. So we patterned this into wires and through electrical contacts. And the measurement works by passing an RF current through the wire. This generates an RF spin current due to the spin Hall effect. And this gets injected into the ferromagnetic layer where we generate an RF torque. And then we sweep the magnetic field through the ferromagnetic resonance of the permalloy film. And at resonance, the magnetization oscillates at the same RF frequency that we apply to our sample. And this this oscillation generates an RF resistance due to the anisotropic magnetoresistance, which mixes with the RF current to get a DC mixing voltage, which is what we measure here in this plot. And the mixing voltage is composed of a symmetric and an antisymmetric component. In this case, we care more about the antisymmetric component because the symmetric one is relatively small. And then we can do this whole measurement as a function of the angle between the RF current and the magnetic field. And that allows us to extract the torque geometries. So for only conventional torques, we expect the sine 2 phi cosine phi behavior of the antisymmetric component as a function of the angle. For the unconventional part, which would be a spin polarization parallel to the current, we expect the sine 2 phi sine phi behavior. And then for a combination of the two, we get something that combines the both angular dependencies. So what do we expect if the spin polarization follows the magnetization? So we set the magnetization to be along the magnetic easy axis, the 1 bar 1 0 direction. So if we apply a current along the 0 0 1 direction, which we say is theta equals 0 degrees, we expect only conventional torques because the spin polarization would be perpendicular to the current along the easy axis, which is the conventional case. But if we apply current along the 1 bar 1 1 direction, which is the positive 54.7 degrees, we expect positive unconventional torques because the spin polarization would have a component parallel to the current. And then for the opposite angle, we expect negative torques because the spin polarization would have a component anti-parallel to the current, or to the current. So this is the geometries we would expect: negative unconventional torques, no unconventional torques, and then positive unconventional torques. So when we measure this for the ordered chromium platinum 3, this is actually what we see. So for 0 degrees, we see no unconventional torques, only conventional ones. For the negative 54.7 degrees, we see a negative unconventional torques. For the positive 54.7, we see a positive unconventional torque. So this is what we would expect if the torques is generated from the magnetic order. However, we also looked at the 90-degree case where the current is parallel to the magnetic easy axis, and this is where we would expect the largest unconventional torque. But what we actually see is there's no qualitative difference between 0 and 90 degrees, so this already suggests that magnetism doesn't play a role in generating these torques. And we further confirm this by measuring the disordered sample that's paramagnetic, so there is no magnetic ordering, and we see exactly the same results as for the ordered sample, which again suggests that there's the magnetism is not involved in generating these unconventional torques. So the question is, what's actually happening if the magnetism is not involved? And for this, we talked to our theory collaborators who worked on a theory to explain how this works. I'm not an expert in this, so I'll just summarize what they found out. So they say that the indirect non-local spin-orbit torque mechanism is responsible for this, and there's actually an archive paper by them specifically for this indirect non-local spin-orbit torque that doesn't involve unconventional torques, but it explains kind of a similar mechanism. So the way that this works is that the spin polarized current from permalloy leaks through the copper into the chromium platinum 3, which I just indicate here. So there's a current that flows also through the permalloy, which we apply with the RF current, and that leaks through the copper and chromium platinum 3 to this chromium platinum 3 interface. And the spin polarization of this is along the magnetization direction of the permalloy. Then at the copper chromium platinum 3 interface, we get spin-to-spin conversion due to spin orbit scattering. So spins get converted from one polarization and travel direction to another polarization and travel direction. So the current is converted to an out-of-plane spin current, where now the spin polarization is along the magnetization of permalloy crossed with this vector F. And this vector F depends on the symmetry of the chromium platinum 3 copper interface. So with different symmetries, we get different vectors F, and then we get different spin polarizations depending on the symmetry. So how does this work? So we have two mirror symmetries in the chromium platinum 3 crystal structure, and this is independent of whether we have ordered or disordered chromium platinum 3. So one is along the 001, which was the 0 degree case, and one is along the 1 bar 10, which was the 90 degree case. And if we apply current along these two directions, then the vector F is such that the spin polarization only has a conventional direction and no unconventional one. But if we apply current not parallel to these mirror planes, like in the negative 54.7 and positive 54.7 degrees, then F is such that the spin polarization can take on a component that is along the current direction. So this is what explains how we can get unconventional torques in both ordered and disordered samples without the role of magnetism involved. So to summarize the talk, we measured unconventional field-like spin torques in both ordered, which is ferromagnetic chromium platinum 3, and disordered, which is paramagnetic chromium platinum 3. And we attribute these unconventional torques from the non-local indirect mechanism I just mentioned. And yeah, if you want to see more, especially on the theory part, you can check out our archive paper on this. And this was also recently accepted in Physical Review Applied, so you can also look there for more information soon once it's published. And then, of course, you can also send me an email if you have any more interesting or any more interest in this. So yeah, thank you for your attention. And,
thank you, Robin, for such a nice talk, nice discussion. So we have time for questions. If anyone has any questions, he can unmute himself or put the question in the chat box. So, Robin, actually, I have one question. So the question is, so you said that you fabricate chromium platinum on MgO at 500 degrees Celsius, right? If I remember correctly, right?
Yes.
But then you need to go at very high temperature, around 800 degrees Celsius, in order to have this atomic ordering.
Yes.
So my question is, even like 500 degrees Celsius is still very high temperature. And why you are not getting the desired ordering, although it's crystalline, but not proper ordering? But at this high temperature, 850 degrees Celsius, is generally considered not as a very good temperature for metals, because metal generally have some stress or some other, surface related effects at such a high temperature.
Yeah.
So what do you think about it? What are your comments about this? I mean, why it requires so much high temperature to have this ordering?
Yeah, so I'm not completely sure why that is exactly the case. I would assume that the high temperature, that maybe 500 degrees is not quite enough energy for the atoms to arrange themselves in the ordered phase, and that the 850 degrees is more suitable for that. So I've worked on another material which is kind of different, but it's manganese 3 platinum, which also needs relatively high temperature to grow a very nice ordered crystal structure. So yeah, I don't know exactly the reason behind it, but yeah, that's what we see in this case.
Have you measured any surface roughness or anything after 850 degrees Celsius? I mean, if surface is good even at 500 and 850, then I believe it's good. But I mean, in my experience, such a high temperature generally degrades some surface, like surface morphology become very rough. And interface property will be severely degraded.
Yeah, so I think the roughness is relatively good in both cases, because the properties of the film are good, and then we also grow a relatively thin copper layer on top of this, and we see no effect of magnetism from the chromium platinum 3 on the ferromagnet. So I would assume that there's no like pinholes due to roughness in the copper. So yeah, we did measure the roughness and it's not extraordinary, or it's not very high. Yeah.
Okay. So we don't have any more questions, and thank you, Robin. Thank you for the
Thank you.
discussion.